Section: Introduction. In this section, we will discuss the challenges of scaling large language models, LLMs. It is difficult due to the need for significant computational resources and high-quality datasets. Typically, pre-training involves using multi-billion parameter models and training with trillions of tokens. However, in our study, we explore the potential of pre-training smaller base language models, LMs, with 1.5 billion parameters using only 1 billion tokens of pre-training data. Our approach focuses on developing small base LMs from existing large reference LMs when only a small portion of the pre-training data is available. This is crucial because many large models have their weights accessible, but not the full pre-training datasets. Our method is straightforward. We retain the initial transformer blocks of the large reference LM and conduct pre-training on the limited dataset, iterating over the data multiple times. This method is efficient in terms of data and computation, as we trained it on a single A6000 GPU in under 12 hours, which is half the time needed for BERT pre-training from scratch. We thoroughly examined our approach in 3 different scenarios, starting from large reference models, training models of various sizes with 1 billion data, and training a 1.5 billion parameter model using slightly larger subsets of pre-training data. We compared its performance with a model trained on 1 billion tokens but for multiple epochs. In summary, our main findings are as follows. We introduce a pre-training technique called Inheritune, where we train a smaller target model extracted from a larger reference LM. By utilizing this method, our small base LM achieves high accuracy on various tasks and scores well compared to larger models. We also demonstrate the effectiveness of Inheritune with different subsets of pre-training data and larger reference models. Additionally, we show that smaller models derived using Inheritune exhibit lower validation loss compared to models trained from scratch for twice the number of steps. Section Summary. In this section, we introduce a pre-training method called MathsF Inheritune, where we train a smaller target model extracted from a larger reference LM, achieving 89% average downstream accuracy on 9 datasets and 94% MNLU 5-shot score compared to the larger model. By training our 1.5B parameter model on just 1B tokens for 8 epochs, we show that our approach is efficient and can yield comparable performance to models pre-trained with significantly more data. Section. We initialize the target model $M_text TGT with the first $N layers of the $M_text ref Thus the weights of $M_text TGT are $theta_0, theta_1, L dots, theta_N1, In this section, we start by inheriting the initial layers of the reference model to initialize our target model. We then proceed to train the model for a specific number of epochs using the available training data. Our goal is to create a smaller language model in a low data scenario by utilizing only a small fraction of pre-training data, which is significantly less compared to the original training data. For our experiments, we use a subset of the RedPajama v1 dataset, which includes data from various domains such as Common Crawl, Wikipedia, books, and others. The dataset proportions align with the recommendations in Llama and are consistent with the pre-training of our reference LM, OpenLLaMA3B. We employ the OpenLLaMA3B version 1 as the reference model for our evaluations. This model has 26 layers, and we focus on a subset of 13 layers for our analysis. We train the model for 8 epochs with a specific batch size, guided by our analysis results. To assess the effectiveness of our approach, we compare our derived model with other baseline models of similar size. These baseline models, such as MPT 1.3b and shared LLaMA 1.3b, are selected based on their pre-training data and number of parameters. We also consider models like OPT 1.3b and PyTHIA 1.3b, which have been pre-trained on datasets similar to RedPajama. Our evaluation methodology includes measuring few-shot accuracy on various downstream tasks to evaluate the quality of the base language models. We assess tasks related to common sense reasoning, natural language understanding, factuality, and language inference using 0-shot and 5-shot performance metrics on different datasets. This evaluation framework helps us compare the performance of our model with existing models effectively. Section Summary. In this section, we initialize the target model with the first layers of a reference model and train it for a specified number of epochs on available training data. We focus on developing a small base language model using a very small fraction of pre-training data, which results in a competitive model compared to existing large base language models. The experimental setup involves utilizing subsets of datasets from various domains and training the model with specific configurations to evaluate its efficacy using the proposed technique. Section. We provide a visual summary of our main results in figure, accompanied by a comprehensive evaluation of performance, broken down by tasks, in table. In this section, we present our findings based on the 1B data we used. We have summarized our main results visually in a figure and provided a detailed evaluation of our performance across different tasks in a table. We compared our model to publicly available baseline models and found that our 1.5B model, created using MathsF and Heratune, outperforms in 7 out of 10 tasks when compared to a reference language model twice its size and trained on 1,000 times more data. We also compared our model to other base LMs of similar size trained on 50 to 300 times more data and found favorable results, which we have highlighted in bold in our table. Furthermore, we compared our small LM to an MPT 1.3B model trained from scratch with 200B tokens and found that we achieved 97% accuracy in all 9 downstream tasks, matching the MMLU 5-shot score. When compared to 2 other small base LMs trained with different large datasets, we outperformed them in the MMLU 5-shot score and performed similarly in the other 9 datasets. Additionally, we discussed the differences between our training approach and a pruning technique called shared LLAMA. Our method focuses on initialization rather than pruning, which requires retraining. While pruning typically starts from larger models, MathsF and Heratune pre-trains a model from scratch with a better initialization method. Although pruning techniques like shared LLAMA require significant computational resources, our approach trains efficiently with just one A6000 GPU for less than 12 hours using 1B data to develop a small base LM. We also explored how MathsF and Heratune performs with different choices of N, the number of layers, while using the same 1B token dataset. We developed 8 models with varying values of N and found that as N increases, the performance generally improves. However, we noticed a slight decrease in performance with 20 layers, possibly due to overfitting. Further investigation into the optimal choice of N, potentially in combination with varying the number of training tokens, and evaluating on a wider range of tasks, is left for future research. Section Summary. In this section, we present our results based on training a 1.5B model using MathsF and Heratune, showcasing its superior performance in 7 out of 10 tasks compared to larger reference models. We also compare our model with others trained from scratch, demonstrating its efficiency in sample utilization. Additionally, we discuss how MathsF and Heratune compares favorably with a pruning technique called shared LLAMA, showing competitive scores despite using significantly less data and compute resources. Lastly, we explore the scalability of MathsF and Heratune across different model sizes by varying the number of layers, observing a positive trend in performance with a slight decrease in larger models potentially due to overfitting. Section. Additional analysis with larger reference LMs and 50B data. In this section, we conducted additional analysis using larger reference language models, LMs, and 50 billion tokens of data. We wanted to see how the performance of our model, in Heratune, is affected when more tokens are available. Initially, we used 1 billion tokens, 0.1% of the data, for our main results. Now, We increased this to a 50 billion subset, 5% of the data, for analysis. We also included larger base LMs with 7 billion parameters as reference models. We observed a clear improvement in the overall MMLU 5-shot score with more data, as shown in the figure. Interestingly, when we used 1.5 billion or 1.6 billion models developed with Inheritune and fed them with the 50 billion subset of fresh tokens, we saw even greater improvements. We presented a table showing the best MMLU 5-shot scores achieved using different reference LMs. For training our smaller base LMs with larger reference LMs, we used 7 layers. We then ran ablations to determine the total number of epochs for training our 1.5 billion or 1.6 billion LM. We found that repetition during training was helpful, especially for MMLU. The performance peaked at 5 epochs for most datasets, except MMLU, and then declined. Some previous studies have shown that the scaling of downstream tasks with data is not always linear. Next, we addressed the question of whether to reuse 1 billion tokens for multiple epochs or use fresh tokens each time. Previous work suggested repeating the dataset up to 4 epochs if it is reasonably large. However, in our study, we found that it is safe to reuse 1 billion tokens for up to 10 to 20 epochs. This phenomenon requires further investigation in the future. The models discussed in the table are saved checkpoints during training and not the final models. In the following section, we explored the performance of Inheritune in a different setting where we had both the larger reference base model and the entire dataset used to train that model. We aimed to see if the smaller base LMs we created could match the performance of the larger reference LM. This was different from our previous setup where the smaller models performed significantly worse than the reference models. For this experiment, we used GPT-2 large and GPT-2 medium models with the Open Web Text dataset. We trained the full 36-layer GPT-2 large model on the training set and evaluated its validation loss. We then applied Inheritune v2 to create an 18-layer model and compared its validation loss with the reference model. If the validation loss of our model was worse, we increased the number of layers until we achieved similar validation loss. We also trained a randomly initialized 18-layer model for comparison. Section Summary. In this section, we analyze the impact of using larger reference language models, LMs, and 50B data on the performance of MathsF Inheritune. By increasing the number of tokens available for training, we observe clear improvements in the MMLU 5-shot scores, especially when developing 1.5B or 1.6B models with MathsF Inheritune, using larger reference models. Additionally, we explore the question of whether to repeat tokens during training, finding that reusing 1B tokens for up to 10 to 20 epochs can be beneficial for model performance. Section: Results and Discussions. In this section, we present our findings and discussions. We discovered that we can extract a smaller target LM with fewer layers from the GPT-2 family without sacrificing performance in validation loss. Additionally, we found that a target LM created using a larger reference LM with MathsF Inheritune shows similar zero-shot performance on 2 relevant downstream tasks. Our results indicate that the target LM developed with MathsF Inheritune outperforms a similar-sized model, especially when trained from scratch. This aligns with our findings in a limited data setting, where we demonstrated that a small base LM derived with MathsF Inheritune matches the performance of similar-sized models trained from scratch on large datasets. Interestingly, our target model trained with MathsF Inheritune for 100K steps performs better than a model pre-trained from scratch for 200K steps. We also observed that the LMs derived with MathsF Inheritune converge as quickly as their larger reference models, despite being smaller in size. Furthermore, we conducted extensive experiments with GPT-2 Medium 355M to explore the impact of initialization on transformer blocks on generalization and convergence speed during pre-training. We emphasize that the initialization of both attention and MLP weights plays a crucial role in the performance of the models. Surprisingly, initializing either the attention or MLP weights led to similar improvements in both convergence speed and final validation loss. When it comes to training small base LMs, conventional methods involve training them from scratch with a large amount of data, which is computationally expensive and time-consuming. We propose that small base LMs can be trained more efficiently and faster with better initialization and multiple passes over the data. Our pre-training dataset consists of 1B tokens randomly sampled from RedPajama, without the need for extensive data curation. In the context of model compression, pruning weights from pre-trained networks has been effective in reducing memory usage in small neural networks and convolutional neural networks. However, there is limited research on applying similar pruning techniques to large language models due to the complexity of the functions they aim to learn during pre-training. Regarding knowledge distillation, previous works have explored initializing student networks with a few layers from teacher networks and then distilling knowledge from the teacher. We introduce MathsF Inheritune as an algorithm that efficiently trains small base LMs using minimal computational resources. We extensively analyze MathsF Inheritune in both low data and full data regimes, showcasing its effectiveness in multitask pre-training setups. Section Summary. In this section, we demonstrate that smaller target language models, LMs, can be extracted without sacrificing performance from the GPT-2 family, and that LMs crafted using a larger reference LM through MathsF Inheritune show comparable zero-shot performance on downstream tasks. Our results indicate that LMs developed with MathsF Inheritune outperform similar-sized models, especially when trained from scratch, and show fast convergence rates even when smaller compared to their reference models. Additionally, we discuss the advantages of initializing both attention and MLP weights in the pre-training phase, highlighting the efficiency of MathsF Inheritune in training small base LMs with minimal computational resources. Section: Initialization. In this section, we will discuss some recent works in transformers that focus on weight initialization to speed up fine-tuning in vision tasks. However, it has been observed that the attention patterns in pre-trained models for vision and language tasks are different. Therefore, an initialization method that works well for vision tasks may not necessarily work well for language tasks. Another recent work achieved improved performance in domain-specific tasks by using weights from an existing model. However, this work also utilized high-quality synthetic data for fine-tuning. In contrast, our approach does not rely on high-quality data. Instead, we randomly sample a small subset of pre-training data used for training a large base language model. Our work has several key implications. Firstly, we enable the cost-effective and straightforward development of small base language models. Pre-training a small base language model with 1 to 2 billion parameters from scratch can be extremely expensive. For example, models like MPT 1.3b and PyTHIA 1.4b require a significant amount of GPU resources and time for pre-training. In comparison, our 1.5b LM variant shows competitive performance despite being trained on a single GPU for less than 12 hours. Typically, small base language models are fine-tuned for specific tasks before deployment. With our approach, called Inheritune, we provide a simple and affordable way to develop a small base language model for later fine-tuning. Moreover, we introduce a naive baseline for pre-training scaled-down versions of large language models. Usually, smaller variants of large language models are pre-trained using the same data. Our method offers a new perspective on determining the appropriate depth of a model without sacrificing generalization on a validation set. We demonstrate that even with a small fraction of pre-training data and a few initial layers from a large base language model, a small base model can be developed. Therefore, our Inheritune approach has the potential to become a standard baseline for any pre-training process aiming to create a smaller variant of a large language model. Additionally, we address the issue of determining the optimal depth for larger language models. The total number of layers in a language model is often chosen arbitrarily. We introduce Inheritune v2 which can help identify the appropriate depth of a model without compromising pre-training validation performance. Our approach can be extended beyond depth considerations.